Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Reza Farrel Ramdhani. I am from Physic, Islamic State University of Sunan Gunung Jati Bandung. And today I will explain my science project in Physic as a part of International Walisongo Science Competition. This project is a coupled spring pendulum system. Okay, now let's continue with the discussion. And the first question is how many constraints in the system? So there are two constraints in coupled spring pendulum system. The first one is the length of rope L1 and the second one is length of spring L2 plus X. The next question, how many degrees of freedom? So there are 2 degrees of freedom in this system. It because the two independent coordinates are required to determine the position of pendulum. So the first one is angle of main pendulum, theta 1, and the second one is the angle of second pendulum, theta 2. The unstretched length of the spring is L2, and the extended spring extends the length by X. Okay, now let's assume the rope and a spring has a very small mass, so it can be neglected. Okay, now we will find the equation of motion in coupled spring pendulum system using Lagrange equation. Okay, the first thing to do is we need to determine the position of each mass in mass 1 and mass 2. Okay, the position of mass 1 in x-axis is x1 is equal to L1 sin theta. We can use the trigonometry to find x1 because of the x1 is in front of the angle, so x1 become x1 equal to L1 sin theta. Okay, if we derivate this with respect to the time, so we will have the x1 dot. X1 dot is equal to L1 cos theta 1 dot. Okay, now if we square this x1 dot, it will equal to L1 square cos square theta 1 dot square. Okay, for the y-axis, the y1 is equal to minus L cos theta. Why it is minus? It is because the position of y is below the coordinate, so it is become minus L1 cos theta. This we can also use the trigonometry to find y1. It is because the y is beside the angle, so it is become minus L1 cos theta. If we derivate this with respect to the time, we will have y1 dot is equal to L1 sin theta 1 dot. If the y1 dot we square, it is equal to L1 square sin square theta 1 and theta 1 dot. Okay, next the position of mass 2 using the same step as before. We will have the x-axis and y-axis. Okay, next we will find the kinetic and potential energy. Before we find the kinetic energy, we have to determine the velocity, where the velocity is x dot plus y dot. If we square the velocity, so it will equal to x dot plus y dot square. So for the mass 1, we can sum the variable that we have before. So x1 dot square plus y1 dot square is equal to L1 square theta dot 1 square. And for the mass 2, x2 dot square plus y2 dot square, it will equal to this equation. So if we already have the velocity, we can put all of this for mass 1 and mass 2 to the kinetic energy, where the kinetic energy is T is equal to half mv square, mv1 square and mv2 square. So we just need to substitute this velocity that we have before to this, and for the mesh 2 also same. Substitute this into the kinetic energy. So the kinetic energy is equal to this equation. Okay, same like kinetic energy, the potential energy is equal to mgy1 plus mgy2 plus half kx squared. This come from the spring constant, so there is a half kx squared. We just need to put the y1 and y2 into this equation, so we have the potential energy is equal to this equation. Okay, after we got the kinetic and potential energy, now next step is we'll put that into the Lagrange function, where L is equal to T min V, kinetic minus potential. So we just need to substitute the T from before and the V also from before to have this. It is the T until this, and it is minus potential energy. If we write again the Lagrange function, it will become this equation. After we have the Lagrange function, the next step is we need to determine the Lagrange equation. So in this system, there are 3 Lagrange equations. Okay, the next step, we'll find the Lagrange equation for angle 1. If the L function we derive with respect to theta 1, we got this equation. And if the Lagrange function we derive with respect to theta 1 dot, we got this equation. Okay, if these 2 equations we put into the first Lagrange equation, this, so it will become this, and we have this equation. If we using the same step to find the Lagrange equation for angle 2, so it is L function derived with respect to theta 2, we will get this. And if the Lagrange function derived with respect to theta 2 dot, we got this. If we put these 2 equations into the second Lagrange equation, so we have this equation. And if we write again the equation, it will become this equation. To fulfill the first Lagrange equation before, variable theta 2 double dot multiplied by m2 cos theta 1 min theta 2. So it will become this equation. By using the same step, the third Lagrange equation is obtained as follows: x double dot is equal to this equation. Okay, to fulfill the first Lagrange equation before, the variable x double dot this multiplied by m2 sin theta 1 minus theta 2. So this equation is become this. Okay, now if we substitute this first equation and the second equation into the first Lagrange equation, we obtain this. Okay, next, to get the equation of motion at the general coordinate theta 2 according to second Lagrange equation, we can multiply the equation 3, which are this equation 3, by minus cos theta 1 minus theta 2 over m1. So we will obtain the equation this. Then substitute that equation, this equation above, into the second Lagrange equation. So we have this equation. Okay, to get the equation of motion at general coordinates x according to third Lagrange equation, we can multiply the equation 3, this equation 3, by sin theta 1 minus theta 2 over m1. Okay, so the equation will become like this. Then substitute this equation into third Lagrange equation. We have the x double dot equation of motion for x double dot. So the conclusion is there are 3 equations of motion. The first one is theta double dot 1 and theta double dot 2 and x double dot. Okay.